Bismillahirrahmanirrahim. We are starting the new session for the solution of linear PDE. If you remember, in previous session I just solved one example. So now I am going to solve few more examples. So you have the complete understanding that how first order first degree linear PDEs will be solved. So now I am taking another example. This is example number 2 of first order first degree or linear PDE. This is example number 2 which we will discuss now. YZP plus 2xq, YZP plus 2xq is equal to xy. Again, this equation is in its standard form. As I said, now time to take capital P, coefficient of small p is yz, coefficient of small q is 2x, and the term on the right hand side is xy. So now we have the values of capital P, Q, R. So time to write auxiliary equation, that is dx over p means yz equal to dy over 2x equal to dz over xy. So this becomes equation number 2. Then it's time to make three possible pairs. So pair number 1, dx over yz equal to dy over 2x. Then pair number 2, that is dy over 2x equal to dz over xy. Then pair number 3, that is dx over yz equal to dz over xy. Now it's time to simplify if there is any simplification there. So in pair number 1 it is not possible to simplify more because no term is cancelling out. But in this pair I can cancel x with x. So new form is dy over 2 is equal to dz over y. Here, yes, simplification is possible. I can cancel y with y. So now dx over z is equal to dz over x. Now it's time to check that which pairs are solvable. So starting from here, in denominator x and y are there and z is missing. So I do not need z in denominator as well, and here z is there. So it indicates that this pair is not solvable. Now moving on for the second one, y and z are there and x is missing. So I do not need x in denominator as well, and there is no x there. So it means this pair is solvable. Here x and z are there in the numerator, y is missing, so I do not need y in denominator as well, and no y is there, so this pair is also solvable. So now we will solve these pair. So just using separable variable technique, y dy, I am cross multiplying 2 dz, and here I can write x dx is equal to z dz. So both comes out as separable variable cases. So now it's time to integrate. So y square by 2 is equal to 2z plus c1, and here x square by 2 is equal to z square by 2 plus c2. It means I can write this one, y square by 2 minus 2z equal to c1, and x square by 2 minus z square by 2 equal to c2. Once we have c1 and c2, then it's time to write the general representation of the solution of equation 1, that is phi of uv y square by 2 minus 2z comma x square by 2 minus z square by 2 equal to 0. This is the way to represent the solution, general solution of equation number 1. So now taking few more examples just for your practice. I am taking few more examples. So let's moving on to example number 3. Now in previous 2 examples, only 2 pairs were possible to solve. So look at example number 3, PTX plus Q tan Y equal to tan Z. This is example number 3. This is example number 3, PTX tan X plus Q tan Y is equal to tan Z. Again, this is in its standard form. So here capital P is equal to tangent X, capital Q is equal to tangent Y, and capital R is equal to tangent Z. So auxiliary equation will be dx over tangent X equal to dy over tangent Y and dz over tangent Z. This forms equation number 2. Then it's time to make pairs. So dx over tan x equal to dy over tangent y. Then dy over tangent y equal to dz over tangent z. Then dx over tangent x equal to dz over tangent z. Now time for checking the simplification, and there is no simplification exists in all 3 pairs. So now it's time to check that whether pair is solvable or not. X and y are the variables in numerator and z is missing, so we do not need any z in denominator. There is no term of z in the denominator, so this pair is solvable. Again in this pair, y and z are there in the numerator, x is missing, so we do not need x in the denominator, and there is no x in the denominator, so this pair is also solvable. And here y is missing in the numerator, so y is also not there in the denominator, so this pair is also solvable. So in this example all 3 pairs are solvable. So still we will only solve any 2 pairs. As I said that if all 3 pairs are solvable, then there is no need to solve all 3 pairs, just required 2 pairs solvable. So you can solve any 2. So let's say I am solving this and this. So this is the case of, again this is the case of separable variable. So if I write in this form, cos x upon sin x dx. So let me give you the idea why I write this, because tan x in the denominator, so if I move tan x numerator, it becomes cot x. So cot x dx equal to cot y dy. Here it will become cot y dy equal to cot z dz. So cot x means cos x upon sin x dx equal to cos y upon sin y dy. So we can write here cos y upon sin y dy equal to cos z upon sin z dz. Again all these are cases of separable variable, and variables are already separated, so I just integrate these pairs. So here the derivative of sin is cos minus derivative sin x is cos x, and it is there in the numerator, so I write log of sin x equal to log of sin y plus log of c1. instead of C1 I write log of C1. So just think why I write this. Here log of sine y equal to log of sine z plus log of C2. It means log of sine x minus log of sine y equal to log of C1. Here log of sine y minus log of sine z equal to log of C2. So using the property of log, log of sine x upon sine y equal to log of C1, log of sine y upon sine z is equal to log of C2. So why I write log instead of C1 and C2? So if you remember, I told you that it is a property that if you have all the terms of integration with log or more than 90% of the terms with log after integration, then it is fruitful to write the constant of integration with log as well. If you do not write constant with log, still it will be counted as correct. But if you write the constant with log, it will make your later on calculation much more easier. As you see that now I can cancel this log with this log and my C1 will be equal to sine x upon sine y. And here if I cancel log with log, my answer will be sine y upon sine z equal to C2. So this is making our calculation much more easier. So if you will not write the constant of integration with log, still it will be counted as correct. There is no mistake if you are not writing constant of integration with log. But as I said, that writing constant of integration with log is more fruitful instead of writing constant without log. So now the final step, that is writing the answer. So general solution, that is phi of sine x upon sine y and sine y upon sine z equal to 0. So if you, let's say you solve this and this pair, then still it will be correct answer. If you solve this pair and this pair, still it will be counted as correct. So if all three pairs are possible to solve, you are allowed to solve any two pairs. And all answers will be treated as right answers. So let me take some more examples of all three pairs. Let I have an example. This is example number 4. This is x minus AP plus y minus BQ equal to z minus C. This is my example number 4. Again, it is given in its standard form. So capital P is x minus A, capital Q is y minus B, and capital R is z minus C. Then writing the auxiliary equation. Here auxiliary equation is dx over x minus A equal to dy over y minus B equal to dz over z minus C. This is equation number 2. Now it's time to write the pairs. So pair number 1 is dx over x minus A equal to dy over y minus B. This is pair number 1. Then dy over y minus b is equal to dz over z minus c, and then dx over x minus a equal to dz over z minus c. Now it's time to check, does any simplification exist? No simplification is possible, no simplification is possible, no simplification is possible. Remember, simplification means is any term there which is possible to cancel out. Okay. So now check that which pair is solvable. Here z is missing in the numerator, and z is also missing from the denominator, so pair is solvable. Similar here, x is missing, so pair is solvable, and y is missing, pair is solvable. Again, all three pairs are solvable, so it simply means you can solve any two pairs. And again, these are the cases of separable variable. So let me solve this time this and this pair. So in this, if I integrate directly, it means log of x minus a is equal to log of y minus b, because the derivative of x minus a is 1 and it is there in the numerator, derivative of y minus b is there in the numerator, and plus again log of c1 or log of x minus a minus log of y minus b is equal to log of c1. And then similarly the property cancelling log with log, so x minus a over y minus b is equal to c1. And here in this case, log of x minus a equal to log of z minus c plus log of c2. Then simplifying, log of x minus a minus log of z minus c is equal to log of c2. Let's say log of x minus a upon z minus c is log of c2, cancelling log with log. So x minus a upon z minus c is equal to c2, and representing the final answer, phi of x minus a upon y minus b, x minus a upon z minus c equal to 0. Now I am solving one more example, then we will switch our criteria a little bit. And switching criteria means then I will discuss the example with only one possible pair is solvable, only one pair will be solvable. Then how we will get the second answer? This will be the case to learn. So now example number 5. Example 5. Example 5 is y square p minus xyq is equal to x z minus 2y. Again, the given question is in its standard form. So taking the values of capital P is y square, capital Q is minus xy, and capital R is xz minus 2y. Look, I took the minus sign as well. Why? Because in its standard form it is PP plus QQ. So if there is any minus, it will be given to the term. So now the auxiliary equation is dx over y square equal to dy over minus xy equal to dz over x z minus 2y. This is equation number 2. Now time to make pairs. So pair number 1 is dx over y square is equal to dy over minus xy. Pair number 2, dy over minus xy equal to dz over x z minus 2y. Then pair number 3, dx over y square is equal to dz over x z minus 2y. Now it's time to check that any simplification exists or not. So I can cancel y with y. So it means now I have dx over y equal to dy over minus x. Then here I can cancel x with x. So then I have dy over minus y equal to dz over z minus 2y. Here no possibility of simplification exists. So now it's time to check that which pairs are possible to solve. In this case, z is missing in the numerator, so z is also not there in the denominator, so this is possible to solve. Here x is missing in the numerator, x is also missing in the denominator, so this pair is possible to solve. Here y is missing in the numerator and y is there in the denominator, and there is no way to cancel out y, so this pair is not solved. So these two pairs are possible to solve. This is the case of separable variable. So I separated the variables equal to minus y dy. I switch x here and y here. So then if I integrate this x square by 2 equal to minus y square by 2 plus c1 and x square by 2 plus y square by 2 equal to c1. Now in this scenario, it is not possible to make it a case of separable variable. It is not possible to separate variables on either side of equal sign. And remember, whenever we say that separate the variables, it simply means all variables belonging to one variable on one side of equal sign and all variables belonging to second variable will other side on the equal sign. So now how it will be solved? If you remember initially, I told you that in majority of the cases, or around 60 to 70% cases, these pair will be solved through separable variable. As a hint, I told you that if that is not the case, then think about linear solution. That is method number 5 of first order first degree ODE. So now if you look at this carefully, this is the case of linear. I can make it a linear equation. How? If I write it, if I cross multiply in this way, I write dz over dy, then it is better to write it here. Then if I split the numerator, that is dz over dy is equal to z over minus y plus 2y over y. And look, if I write in this way, dz over dy plus z over y is equal to 2, then this will be known as linear in Z. Equation linear in Z. So this is, let's say, equation number 3. So here P is equal to, this P is not this one, this belongs to integrating factor. So you may write a small p, no, small p represents the derivative. So let me write p in this way, p is equal to 1 over y. So now finding integrating factor, it is equal to e to the power integral 1 upon y dy, means e to the power log of y and means y. So multiply equation 3 with y. So it will become y into dz over dy plus z equal to 2y. Closing the formula, dy dy and y into z equal to 2y. Integrating on both sides, integrate with respect to y. Integrating both sides with respect to y. On left hand side we will have yz equal to y square plus c2, or yz minus y square equal to c2. So look, this pair is not solved through reducing separable variable, but we solve this pair by using linear case. So now time to write final answer, that is phi of x square by 2 plus z square by 2 and yz minus y square equal to 0. Okay, now I am leaving one thing to think about for you. Think about this, that is it possible to solve this pair by any other method? I am writing here as well. Is it possible to solve this pair with any other method? We will discuss other possibilities of this pair in our live session. So now it's time to write few practice problems relating to what we learned in these sessions. So I am writing few practice problems for you now before ending this session. It's time to write practice problems. So let me write few practice problems for you. Number 1, xp plus yq equal to z. Number 2, yzp plus xzq is equal to xy. Number 3, x square p plus y square q equal to z square. Number 4, p plus q equal to 1. Number 5, p plus q is equal to sin x. Number 6, 2p plus 3q equal to 1. And number 7, a p plus q equal to Z. I write these examples, and these all examples belongs to previous session and this session. Means in all examples you will find that either all three pairs are possible to solve or any two pairs are possible to solve. Then from the next session we will start with the examples when only one pair is possible to solve. So in the next session we will discuss that when only one pair is possible to solve, then how we will solve the second pair. So as far as this session is concerned, it is goodbye. It's time to say Allah Hafiz.